All right, welcome everyone. My name is Ramon, and I am going to be your presenter for this session. Thank you very much for deciding to spending the next 90 minutes with me. I hope I live up to the expectations. So, what are we going to be talking about today? We're going to be talking about how to build a flexible robot brain one bit at a time. You probably noticed that I used a clever trick with emojis because otherwise I was going to have a title of 3 levels, and that was just a little bit too much. So to be able to understand robots, we need to go a little bit back. And when I say a little bit, I actually mean a lot. Does anybody recognize this thing here? Has anybody heard of this?
The copper golem from Greek philosophy?
Yes.
Yep.
Name?
It's like Talos or
Yes,
something like that.
yes. So for those of you, I am so glad somebody found it. So Talos, for those of you who don't know, it was emerging from the resonances of the industrious cultural developments of the Bronze Age. The Greek mythological creature Talos is the embodiment of a metallic automation in humanoid form. In other words, Talos can loosely be equated to the representation of a bronze robot in Greek mythology. Culturally, the massive automation symbolized the potential of human invention and divine intervention during this period of rapid cultural development. This is probably what we would want from robots. We would want some sort of divine intervention and have them help us in ways that we couldn't even foresee before. But the reality is that, think about it this way. If we were to place Talos in this day and age, Talos would most likely be running late for work. And you cannot see the wording at the bottom. It says Talos running late for work in ancient Greek mythology. But yeah, if we go a little bit further, does anybody recognize this too? Okay, fine. That's completely fine. So this guy here, his name is Albertus Magnus. And he lived circa 1200 to 1280. Somewhere around that time. So very weird to see people live about 80 years back then. But he's also known as Saint Albert the Great, Albert of Swabia, or Albert of Cologne, which was a German Dominican friar, philosopher, scientist, and bishop, considered one of the greatest medieval philosophers and thinkers of his time. And then that head that you saw on the second on the side that he was talking to is a brazen head, brass or bronze head, which was a legendary automation in the Middle Ages to the early modern period, whose ownership was ascribed to late medieval scholars such as Roger Bacon, who had developed a reputation as wizards, made of brass or bronze. The male head was variously mechanical or magical. So robots are not a thing from now. We also had washing machines from the 1800s, where you will have a mechanical apparatus at the top that will help you move the clothes that was inside with whatever the heck you put in there. I don't even know that we had soap back then, but hopefully we did have something. And then, if we go a little bit closer to today, you might recognize this thing. Who here has a Roomba? Yes, my man. Yes. Awesome. Well, you also might have noticed that it says iRobot there. I wonder what else is closer to us that has the word iRobot. I don't know. So the reality is that even though we have computers today, like big modern computers, like for example, the Apple one, which was one of the first desktop ones, or even Game Boys, which have a device that potentially could hold some sort of system in it, some sort of machine could come up from that. Well, or even Arduinos as well. Like we have motherboards, we have laptops, we have Game Boys, we have devices. All these tools, they do exactly what they are programmed for. But what if we could put intelligence inside of each of these devices? And can we make it so that we can have some banter at home by the time we get there and talk to the Roomba, the washing machine, or the fridge? Can we make it so that we can get dishes done and put away while discussing the news with our appliances? Or can we do meal prep without doing it? Can the coffee be ready before us as it gives us the schedule for the day and so on? So that's kind of like a little bit of motivation as to why we might want robots or why we might want to give the gift of intelligence to different devices, to different appliances. So, and the goal, can we make robots less dumb? So, and a little picture here. While I was trying to make this with AI, there's a second thing that comes out of there. And I don't know if that's his doppelganger or his twin brother or whatnot, but that's kind of the vision you get. A little toaster over here. So this is the company that I work for. Our name is Menlo Research Lab. And that is actually our logo, the Anti-Dumb Robot Club. So my role there, who am I? I am currently a research engineer at Menlo. Previously, I was in developer relations. I lived in the UK for that. I was a software developer, tech educator, researcher in economics and machine learning and management sciences. For personal side, I love coffee. I love mountain biking. I am from the Dominican Republic. I've lived in Kansas City, Washington, D.C., Australia, London, and then back to Australia. And my passport now looks like that kangaroo's passport over there. For all the traveling that I've done. So what are we going to be doing today? We're going to be talking about AI models and touch on a little bit of constrained hardwares. And I'm going to give you some examples with C++. I'm going to give you some examples with Python. And all throughout the session, I'm going to be giving you examples. So I figured as I've been coding in C++ since the beginning of the year. So I'm probably the least, what's the word that I'm looking for? Qualified to teach you something about it, but I can definitely learn alongside all of you. So I have some tutorials here that I think are very useful to think about how to put these AI systems or LLMs or diffusion models or whatever you want to call them today. We're going to also put them apart. But my hope is that by the end of today, you have at least a few key things that you can take from here and then use whenever you are programming in C++, and then you think about a robot, you think about AI, and so on. So then we're going to talk about the tool that I've been helping develop, which is called Cortex.cpp. We're going to do an architecture deep dive. I've rearranged a couple of things, so we might do more than just touch on the architecture. There's a lot of stuff there. C++ and Python interoperability. And then some examples, research, trade-offs, and then the future of where we see robots headed. All right, so part one, AI models on constrained devices. So if you think about the breakdown of a robot, can I ask here, what are the components that you think a robot has? Anybody? Throw anything at me.
Sensors.
Sensors, yes. What else?
Physical motor.
Yes. What else? So we need
An artificial intelligence.
Well, maybe, yeah. Well, right now, a lot of them don't necessarily have something that you could call artificial intelligence. They have bits and pieces. So there's two aspects of machine learning that is important to separate. There's many aspects of artificial intelligence that are important to separate. I'm going to separate two. One is there's very narrow intelligence where you have systems that do one thing and one thing only. The typical example is the spam versus non-spam emails. The accept alone versus don't accept alone, recognize an object in an image, only that object. Everything else is false. And then there's also the systems that you can interact with and have a conversation and have them output actions for a robot. But yes, artificial intelligence. And then, so I'll tell you the 5 that I have here. It is possible that there could be more, but body and actuation. So the rigid structure, joints, motors. I'm sure some of you, if not all of you, have seen the videos of the robot from Boston Dynamics, which is absolutely unbelievable to see this thing do parkour and so on. I can barely jump on that table. And sensing, I can actually jump on that table. Sensing, cameras, encoders, lidars, whatever you want to call it. Anything that can give you input about what's happening in this world. Compute, controls, CPUs, MCUs, GPUs, RTOs, roads. And I was going to put here, just to mess with people, some other acronyms that had nothing to do with anything, just to trip people up, but then I did. Energy, batteries, or main supplies feeding everything. So they have to be powered up at some point and in some way. And then the last one, communication and I/O. So buses, Wi-Fi, UI devices linking the robot to human, to the cloud and whatnot, whatever it might be using. So those are the broad 5 categories: body, sensors, compute, energy, and communication. All right, so when we think about AI models, you might recognize this whale. Does anybody recognize? Yeah, okay, cool. And what about this one? What about that one? Oh yeah, I put it there. That one as well. Perplexity. Has anybody used Perplexity here? No. Okay, download it right now. It is the way I used to describe it, not anymore, is if Google and ChatGPT had a baby. But now that ChatGPT has search in it and Google has Gemini and it also has search in it, then it's all the lines are getting blurry, but they still have a solid product to me. Quen, does anybody recognize Quen or have heard of it? No? Okay. Those are the best. They have the best family of open source models in the market right now, things that you can run on device without losing a whole lot of intelligence. And then Gemini, the one by Google. Now, I'm going to ask this, very provocative a little bit. Is there anything that might be very similar out of all of these logos?
Yeah. You're all star-shaped.
I thought of something else. I just found this article the other day and it says if you pay attention to AI companies' branding, you'll notice patterns, circular shapes, often with a gradient, central opening or focal point, radiating elements from the center, soft organic curves. Sounds familiar? It should. So I thought it was hilarious when I read that and I said, I have to put it here. I hope that doesn't go against the code of conduct. I just wanted to make people laugh here. Okay, so for the first example that I have, so if you are communicating with LLMs or with models that come from the organizations that I just showed you, they are very useful. They are, all of the ones that I showed you have, all of the companies that I show you have at least one state-of-the-art model. That means that these are the most intelligent AI systems that you can find. They started as plain LLMs, so systems that take input as text and output text back. And nowadays they take in different modalities. They take sound, they take videos, they take images. And also, so now you have behind the scenes, when you're talking to one of the systems where you're in ChatGPT and Gemini and so on, you're talking most likely to a system full of tools, full of things that can use rather than a model alone in isolation itself. But either way, when you are trying to talk to a model, you usually have to make a request of some sort. And if you haven't done it from the command line, it looks something like this. You have your headers, you have your API key, you have the version of the model that you might be using. This is an example from the Anthropic one, the content application. But then I wanted to, as you can tell already by my style, I'm here just to make you laugh. I'm not going to teach you anything. And so I put, can you please create a rap song about CPP now? It should be cool, catchy, without any explicit content. And most importantly, it should leave people wanting more songs like this one. Pick a C++, pick on C++ a little bit, bring in a little bit of the feud with Rust, mention Zig and other languages that might have some interesting comparison with C++, especially hot takes. Actually, hot takes all day, please. So let's see what he came up with. And actually, instead of just showing you all of the stuff that he blabbered out to me, let me actually show you the song. Because there are other systems that allow you to create music, create sound, take words, and then output a audio file. And so that's what I did. And I have two here. So let's go with the first one. Let's see. I think it's only going to come out of my laptop, but let's see. I'm going to put it very, very loud so that everybody can hear it. Hopefully I don't explode my speaker.
Rolling up to Aspen, cold in my mind. CPE now conference, best of its kind. Templates and pointers, memory leaves too. 5 days of syntax that flow through review. Yawning in the building, standards committee. Making decisions that are oh so gritty. Flush down. With the brackets flush down. With the brackets flush. Memory management got you stressed out, y'all. Flush down. Rust gang coming through with their ownership rules. Talking about safety like we're coding fools. But C++ been here since '83. Legacy code running every.
I just thought it was hilarious. The Rush people coming with their safety stuff, like we're fools and stuff. And then the other one, it was actually quite cool as well.
Rolling up to Aspen, code in my mind. Seek now conference, best of its kind. Templates and pointers, memory leaks too. 5 days of syntax that'll blow through your view. Bjorn in the building, standards committee, making decisions that are.
So it even mentioned Bjorn and Strauss, and it is hilarious. So they are in the repo. So make sure you check them out when you have a chance. Okay, so 2 modalities so far. We mentioned text, we mentioned audio, there's also images. So this one in particular is, look at that. I made the cardinal sin of leaving there an API key because it didn't want to read my environment earlier when I was testing and just left it over there. Go crazy on it. It has $10. This one is using Ideogram. They're a very cool company that has been. I was not trying to go there from here, but anyways, if you're ever interested in making cool images, they're kind of like a competitor of Midjourney. They're very cool. I don't think they are as solid as Midjourney, but they do have a lot of good stuff in it. Okay, so you pass in the URL, you send a curl request. With images, you're very often going to have to provide additional parameters because you want to control the aspect ratio, you want to control whether a lot of these models, the way in which they get, or these systems, the way in which they get a really cool image that almost seems magical is a lot of times by taking your prompt and making an even better one. So if you put auto in this one, in particular, the magic prompt option is going to rearrange your gibberish and make it even better. At least it did for me. And then he came up with this one. I didn't really like it, and also I said 2025 and he came up with 2022. So, I mean, it hasn't caught up with times. So for the dubbing one, I don't think I'll be able to demo this one because actually I have. Okay, so C++ can help us create an audio recorder in a relatively straightforward way. So I went through the exercise of finding a lot of stuff to be able to put one together. And in the end, I actually had to get a little bit of help, but I did end up making a very shitty one. And okay, so here we have the cool thing about notebooks. I have not uploaded my, I need to do this. If you have the repo, keep it somewhere. I have to upload the environment so that you can recreate, if you want to code inside a Jupyter notebook without having to do all the ceremony of creating your main function and just run stuff directly from the notebook, you can do that. Okay, so we have quite a few things. The main libraries that I had to find were the port audio and the SND file. So we have a couple of things that we need to define. For example, the sample rate. Does anybody know what a sample rate is? And does anybody know?
It's the number of samples per second.
Yes. And what is the range that the human ear can listen?
Tens of thousands.
I think it's about like, it
depends on the person.
Yeah, it depends on the person. Yeah, that's right. And I think,
20,000.
sorry?
50 to 20,000.
Yeah. It's actually not huge. The range is not huge, but it depends on the person. Some people can actually, capture a little bit more, but that's right.
To do with frequency, right? No.
Sorry?
That's frequency, isn't it? Not sample rate.
Sorry, not the sample rate. That's the frequency. Yes, the hertz. So the frequency is measured in hertz, and then the sample rate is what you are going to use the hertz to divide by, and then you're going to get the seconds. So frames per buffer, how many samples the library port audio is going to process, number of seconds. If you come, I don't have it as a CLI parameter. Again, this is very rudimentary. I don't have it as a CLI parameter. So if you want to use the recorder, you're going to have to come back here, change these seconds and put 10, put 1 minute, put whatever. And then once you run it in the command line, then it's going, and also I don't even have an output file. So bear with me. Recording that WAV. So you can use that. And you can change that so that you can have a different name for your file. Or you can just pass them into a main function and have arguments. So the first one, so we create a struct. So record the data. So we have a vector of floats. We're going to call it record the samples. a dynamically sized vector. We have a recording, which is true, and then the max samples, I'm leaving it at 0 here, or starting it at 0. And then we have the poor audio callback, where there's a lot of stuff happening, but if you want to have a deep dive, I'm going to leave it to you to come here and like read all this stuff, but I mean, we can go through it. So it receives the raw audio for the data in the input device. So that's why I put all these comments here. So the pointer to the raw input file data, the pointer to the output audio, the frames per buffer, the time. Here I have the timing information, the flags about the buffer, over or underflow, and then the pointer to our custom data. So there's a lot of stuff here happening. So I'm going to leave it to you, and I'm going to show you the rest of it. We have for error handling, just in case there's something happens. And then in our main function, we have so the variable declarations, the initialization of poor audio, the error handler function, the input parameters, what we're going to pass in here. And I had this, it's a little bit long, so forgive me. I had to put I had to split it into different files here. The recording for a specific amount of seconds. I'm going to show you an example of what this looks like, and then what I end up doing with it. So it's going to, and yeah, so this is about the whole implementation is about 60, I believe. We have about 158 lines of code to be able to do this. So now, let me actually. So this is, let me actually show you the full implementation of it. So. Gonna do 5 seconds here. So yeah, so this is what it looks like, the full implementation of it. And then I have more examples, a little bit less condensed, where I'm going to show you different kinds of matrix multiplications that we need in order to be able to really squeeze out the performance of a model when we're reading it into memory. And then I'm also going to explain how a lot of companies are running today local models with specific tools like Llama CPP, maybe you have heard of it, and then how we do it in Cortex. But what I wanted to show you here was the, oops, okay. So, hello there, can you hear me? Okay, let's see if that actually came up.
Hello there, can you hear me?
Okay, excellent. So what I wanted to show you with this one was this demo here for the last bit of LLMs, where I'm using something called 11 Labs. And 11 Labs has created some of the coolest voice models in the market. And it allows you to do real-time translation. So who here speaks another language, or a language other than English? What do you speak?
German.
German. And for you?
I speak 2 more languages, Hindi, Odia, and I'm learning French.
Okay, this is great because they have an example. I wanted to do an example, but it takes forever. And what is
German?
German as well. Okay, so they have an example here where they are dubbing from English to Hindi that I really like.
I've interviewed some of the best CEOs in the world, and I'm fascinated by leadership. And the thing that really struck me is that when you think about your leadership style, Australia cricket team की leadership के बारे में सोचते हैं, तो आप अपनी leadership के style को कैसे देखते हैं?
How good is that?
It's correct.
It's correct, right?
Yeah.
It was good. Okay, so that's exactly what I. So if you want to play with it, check it out. I don't think I left. I don't think I left my API key, but they do in this one. there, but they do give you, it did read this one this time. They do give you about 10,000 credits. So if you want to dub anything to German, to Hindi, or whatnot, even a conversation that you're having, like it is phenomenal that it can take your voice and recreate your accent in a different language. Okay, so reading the file here, giving it the target data, and then sending the request. It usually doesn't give you any kind of information back, or there's no waiting, there's no streaming, there's no nothing. So what you have to do is like create a while loop and then let it give you the status. Actually, it's right here. Let it give you the status of the dubbing as it's happening in real time, and then you get a little file that you'll be able to play at the end. Okay, so now we get to the LLMs piece, and then I'm going to be showing you a couple of implementations of major matrix multiplication in C++, and then I'm going to compare them to Python, which is something that we are doing with Cortex, and also when we leverage Llama CPP as well. So we're doing it in both ways, ourselves and also from Llama CPP. So transformers and diffusers, they are kind of this, the AI systems or the AI models that have taken the world by storm. A transformer in and of itself is like a smart reader, and that first understands input text, and then by comparing every word to other words in the prompt or in the context length. So the context length is if you have a brand new notebook and then you haven't written anything in it, the context length of a model is that notebook. Once it gets filled up, it cannot do anything else because it can only reach that length. A lot of times when these models are trained, they can very much go beyond that limit, but machine learning engineers and researchers, what they do is that they figure out when does the model go haywire after a specific amount of context. That's why about 2 years ago, you would only see a context window of about 10,000 words, 8,000 words, or tokens. Tokens are not always a word. They are pieces of a word, and then they make up the context length of a model. But the system works by splitting this process into two parts. One part, it reads and understands. It is called the encoder. It understands what you're giving it, the prompt. Hey, give me a poem, give me a rap song, and so on. And another part writes the responses, the decoder, with both parts using a clever matching system that helps them focus on the most important information at each step. In this day and age, usually people have thrown away the decoder and they use the encoder, and they use the decoder only because it can give you almost the same results as the other one. So encoders are usually very, very good for classification tasks, for name entity recognition. If I create a sentence and I say the stock of Apple went down by $7 last night. $7 is currency, monetary currency. Apple, an organization. Stock, financial term, and so on. So it's getting the entities out, and you can get a table with a lot of information that is useful for financial analysts and for a lot of other people that deal in the financial markets. And then the other one, a diffusion model, works by gradually adding noise to an image until it becomes completely random. And then learning to reverse this process, it creates a new image. What it needs to have two components. It needs to have the image, and it needs to have a description of the image. That description of the image gets sort of translated into similar tokens or similar encodings to the ones of the image. And now we have two things that go hand in hand together. So if something similar comes up, we take a lot of steps to generate an image, and we go from something that is nothing, that is just noise in an image, a lot of pixels with random colors, to then create, after 30, 40, 50, 60 steps, a brand new image. So diffusion model, that's why they're called diffusion. They kind of like mess up the picture and then create a brand new one. Okay, but there are many more models. We're not going to talk about all of those here, but there's many more. Okay, so transformer, what we call, I'm missing an L there, what we call AI today. So they go through 3 stages. One is they take all the data from the internet and a library and then pass it into this model, this giant blob of numbers, this function. So sorry, we pass it through a function, and then we start generating numbers. Those numbers get updated, and what the model learns to do is to predict the next word, the next token in a series of documents. And that series of documents is a corpora of documents from all the internet and all the libraries around the world. At some point, there's estimates out there that say that we're going to run out of data to train LLMs by 2030. I'm not entirely sure if that's correct or not. I don't really have an opinion. That's the first step. In the second step, it's kind of like fine tuning. It's saying like, okay, now that you know how to predict the next word, how can I show you to tell me what I want to do? This is what is called an assistant. This is what you might see on the internet. When you go and talk to a model, you see, oh, you are a helpful assistant everywhere. And that might be the system prompt that a model has. That system prompt tells it, hey, you are meant to help this other person. But that's not really it. That's not really it. What it really is meant to tell the model is, hey, this is your command. This is kind of like your 10 commandments, but it's not, you can put more than 10 in that system prompt. The second piece is that there's a format, and you can think about it as a template. That template has usually something similar to XML tags. So you have a question, it is starting, or a question or a prompt, it is starting, a prompt is ending, an answer is starting, an answer is ending. And we collect many of those instructions where we teach, where we ask a question, where we prompt a system, and then we get their desired response back. Using those, feeding them back into the model, we teach them how to create responses that we like. But in this instance, the model has a lot of knowledge. It has a format in which it can respond to you, but it doesn't know what you like. It doesn't know what makes something a really good response versus a just okay one. So the last piece is alignment with something called reinforcement learning with human feedback. What that is, or what that means is it's not necessarily a fancy term, but it's a term that is used, or it's a way of training a model where we take a data set with prompts and different kinds of answers, and then we have answers that have been rated by a human, and it says, hey, this one is the better one out of the two. Both are good, but this is the better one. So the model now favors different answers versus others, even though both could be good. And companies like Scale AI, Toloka, I think they are based in Toloka AI, they are based in Russia. And then there's a bunch of other companies that they do labeling for companies, especially big AI companies like OpenAI, Anthropic, and so on. And then once you collect these massive amounts of data, then you can use them to then fine tune the model again into something that you want. So what C++ does best is that at the end, at the lowest level of these systems, these AI systems, everything comes down to a matrix multiplication. And sometimes these matrices are so large that what we need to do is to take a space or a small chunk of that matrix, we call it a tile, and then send that tile all the way from, so first we have the model, what we call the weights. These are a lot of numbers, a blob of numbers, a zip file with a lot of numbers. We take it from storage and into RAM. And then from RAM, when we start computing, when you send a prompt to the model, and I'm going to show you what that looks like here in just a second with a couple of nice diagrams. What's going to happen is that the big matrix is going to be split into different tiles, and each tile is going to go down via the cache levels. So we're going to go down the L1 cache, L2 cache, L3 cache, L2 cache, L1 cache, and then the register. In the register, you're going to have a tiny one. But and then depending on the size and the kind of machine that you have, you're going to have more capacity or less capacity. So what does that look like? So say, for example, we have a matrix. We have a vector that has a vector inside of it. So we have a 2D matrix. And then that matrix is going to look like, so the first thing that we're going to do is that we need to check that the dimensions match. If we have two matrices and we're going to multiply them together, we're going to have to be very careful that the columns and the rows match when we start multiplying one by the other. So we check that all of them are matching. We throw an error if they are not matching. And then we're going to create a third matrix. So we're going to multiply A by B, and then we're going to create C. C is also going to be a vector. And then we're going to create a loop where we start from the outer part of the matrix, and then we go to the inner part of the matrix, and then we start multiplying one thing by another. And then we return what we have. So if we want to print it inside a notebook as opposed to printing it on the terminal, so I ran these examples on my laptop. So So I needed a function to be able to print them in the notebook. And it's really nice that you don't have to, like, if you actually want to start testing, start building your classes, building your functions, and you don't necessarily want to be compiling, checking, then you can actually get a lot done by doing interactive programming inside a notebook. With it can only take you so far, I think, especially when the code base gets really, really large. It becomes a little bit difficult to split things apart because everything depends on one another. But either way, check it out if it might help you for your day-to-day work. Okay, so here we have two very simple matrices. In a second, I'm going to create another matrix, a larger matrix with random numbers, and then we're going to compare the speed at which from C++ over 10 loops. We're going to take the average of 10 loops, and then we're going to compare it with the same implementation in Python. So we have a couple of matrices. Everything works fine. We print the matrix. We have matrix A, matrix B. We multiply them, and then we have the expected matrix C. And then now we have another matrix, which is the result of A times B. So far, so good. This is what is happening at the lowest level when we send a prompt to an LLM. An LLM or any kind of, or all of these models, they have something called weights and they have something called parameters. Those parameters are usually set in a very flat file. So, and I'm gonna show you a picture of what those files look like in a second. And then that flat file then needs to be reshaped into different matrices. When an input comes through one side, we send in a vector of data. That vector of data goes throughout all of those matrices, multiplying one by another. And then if they don't fit in memory, we start taking smaller slices of those matrices. So what about Python? In Python, it looks, honestly, when you look at this code and then you look at this one here, I mean, you know, people throw shade at C++, but they're pretty similar. So we check that, we check the matrices, we check the length, all of them. We have a C matrix. I don't know if anybody here has written a lot of Python code or a little bit. We have two list comprehensions inside of one another. So we create an array and inside another array to represent a matrix. And then we iterate over the rows in the same way as we did it with C++. And then we print it, although we didn't really need to do that, just to make sure everything looks exactly as it was before. We have matrix A, we have matrix B, and then we have matrix C. All right, so what are the speed differences between these two approaches? Why do people often go to C++ to be able to squeeze the most out of the hardware? Is it really that Python is slow? Is it really that C++ can give us a lot of advantages? Well, the answer is yes. Even in naive implementations, when you go down to the hardware, then you are going to get a lot of benefits. And a lot of the tools with which these models have been created, they're called PyTorch, TensorFlow. In this day and age, PyTorch has kind of won the battle between the best ML framework out there as of now, until something better comes out and takes over. And the reason being, it's quite fast, and it's not just Python. I'm going to show you a couple of stats in a minute that I looked up for the percentage of code in all of these major tools that have C++ versus Python code. So what are the speed differences? So in C++, I took the exact same code and then the exact same thing that we saw before. And then I generated a random matrix. So of size T, so I have my size, min value, max value, and so on. And then here we create a couple of random numbers, so we generate random numbers to fill in the matrices, and then we multiply them. And then what we do here is that, so we have a matrix of size 100, we can adjust it however we want, and then we have about 10 repetitions. So in the naive implementation, or not the naive implementation, in the main implementation of this, so the matrix of size 100 by 100, repetitions 10. The total time for C++ in 10 repetitions was about 78 milliseconds, but the average C++ time per multiplication was about 7.8 seconds. And this is a very naive implementation. Like, this is not even highly super optimized. But when I show you the exact same thing in Python, what you end up noticing is that it is, so we had 7.9 milliseconds. And in Python, the average is 55.9 milliseconds in a very naive implementation. Yeah.
I noticed you were using float in C++. I thought Python used double precision.
That is correct. But the only, and I mean, yeah, that's right. And the biggest reason for that is that if I go and use, for example, have you heard of NumPy?
Yes.
Yeah, so if you go and use NumPy, then you're accessing kind of like data types directly in C, I believe. So then the comparison doesn't come, it's not kind of like apples to apples anymore. So yeah, so we ended up getting a much slower time. I gotta say, there's a lot of stuff that you can do to optimize both implementations and even get better, much better performance. This is very naive, and it's just to show what is happening behind the scenes. So in industry, everybody uses both. So PyTorch has started in 2016. Today, it has about 32% of the code is C++. I think about 2 years ago, it used to be over 50%, but there's a lot of stuff and a lot of optimizations that people have done, and there's about 53% of that is Python code. It was developed by Meta. Now it belongs to the Linux Foundation. They donated it. Another very good one is XGBoost, and it allows you to use random forest and extreme gradient boost algorithms, which are fantastic for classification and linear regression, or not linear regression, or predicting floating point value. So prices versus classification regression. So about 44% of the code is C++, and 36% is Python code, and it still has something else. I can't remember what it was. So yeah, it started by Tianqi Cheng to compete in Kaggle, and then now today is used by some of the major corporations out there. TensorFlow still has over 50% of code in C++, and then about 36% is Python code. They started porting it to Swift at some point, and then something happened, and now Chris Ladner started a company called Modular, and then they're creating another language called Mojo. And there's a whole other story there, but I believe the Swift project ended up dying, sadly. ONNX, this is a format rather than sort of a framework to train and develop models. But what ONNX allows you to do is to take a model that was trained with PyTorch, with TensorFlow, and something else, or anything else, and then pass it on to a general format that can be brought into with libraries in different languages, into a mobile device, into an edge device, into the browser, and so on. Okay, so hardware requirements. There's a lot of stuff that this looks hideous. Let me show you what this actually looks like. Oh yeah, I did misspell. So Cortex is, I'm going to show it to you now. Hardware. So Cortex is the tool that we are developing at Menlo, and as of now, it powers one of our main applications, which is called Jan. It has been downloaded more than 3 million times last month, and it is a tool to be able to download models and use them locally, offline, if you choose to, without any internet access. And it also allows you to talk to models via APIs from other companies. So you can talk to ChatGPT and you can talk to a local model at the same time. So in my laptop, I have 13 Gen Intel Core i7. I have a NVIDIA RTX 2000 ADA generation. It has about 8 gigs that it says it has for memory RAM, and then that's my driver version. So we make sure that we check what kind of hardware does the host have. That way we can give them the best performance for the models that they download. Llama CPP also does this, and I'm going to show you what that means in a second. So what are the hardware requirements for this massive model? So you usually need a GPU, but because things are evolving very, very rapidly, nowadays you can run on CPU only smallish models and still get a lot of bang for your buck. So if we look at memory at the requirements of these models, when depending on the size that they might have, some of the best models that you can run in your laptop today are some that come by Gemma from Google. They came out about a month and a half ago, and they have different sizes. So they have 1 billion parameters. That's going to be roughly about 0.5 gigabytes. The estimated RAM usage is going to be about 1.5 to 2 gigabytes. The reason for this is this little bastard you see here called the KB cache. I'm going to show you what that is in a second with a diagram. And what that is, the KB cache, is that when you... could that be me? Oh, let's get out of Discord. Okay, so what that means is that the KB cache is that when you send a prompt to a model, what is happening is that the model is paying attention at all of the tokens inside your prompt and all of the tokens that is going to need in order to answer your question. Once it answers your question, it doesn't want to come back and look them up again. But what it wants to do is to sort of have them there ready to go if they need to be reused, because it's going to have to look them up again. The way you converse with a model or get responses back from a language model is by filling out that notebook. And as we fill it up, then it's going to have to remember all the stuff that it has. So that KB cache can grow ridiculously large. And usually when you see online that to run a model locally, you're going to need 5 gigabytes, but the model is actually only 1 or 2, then that is what that means. It means that you're going to have to pay attention to the KB cache if you use it often, especially if you have that model powering other applications that you run only locally. So here, the Gemma family, they come in 1 billion parameters, 4 billion parameters, 12 billion, and 27 billion. The 27 billion one, this is a quantized version that will fit in an RTX 3090, but the reality is that the unquantized version, so this is in 4, QAT stands for Quantization Aware Training, where the model, I think I hope I'm saying this correctly, but you quantize the model, letting it know that it's or using different techniques so that you can hold on to as much knowledge as possible, even though you're downsizing the model and it has less knowledge per se. So the unquantized version of Gemma 27B is about 54 gigabytes. So you're going to need either one of the best GPUs out there, which cost thousands and thousands of dollars, or you can get a quantized version and run it locally, especially the newest M1 and M2 Max. They are fantastic and they allow you to run these models flawlessly. The latest versions of the Qwen models, they just came out yesterday. So this table is not fully up to date. They are unbelievable. They are at par. I have a table showcasing the benchmarks of those models, but they are just on par with the best models 2 years ago, 1 year ago, and actually 4 months ago, maybe even less than that. And you can run them completely locally. There's one of them that have 4 billion parameters, and the full quantized version is about 8 gigabytes, I believe it is, and you can run it anywhere, in any modern computer, even in CPU, even if it's slow. So this is sort of to give you an idea as to what the memory estimation would be for models that have already been quantized. When you go to places like Hugging Face and you run models locally, more often than not, you're going to have to run a quantized version of a model. So if we come here and you put, you could put GGUF, and then you're going to find every model under the sun that has been quantized into GGUF. And you might ask, what the hell is a GGUF, Ramon? So I'm going to show you what that is in just a second. I have a diagram to show you what it is. So you're also going to need storage. And depending on the storage that you use, if you are using a hard disk drive, then that's going to be incredibly slow. I'm going to show you the speed differences for loading a model of 10 gigabytes into RAM in an HDD versus an SSD versus one of the newest NVMEs. It's staggering the time that you will wait just to load the model. So you need to pay attention to storage. You need to pay attention to compute. So earlier I was mentioning, I was going to show you the speed and I was going to show you what is happening with these tiles alongside the thing. So I made this diagram, and here you have the model loading. So the model is going to go from, if you have an NVMe SSD, that's going to load about 3,000 to 7,300 megabytes per second. So we're talking about 3 gigabytes to 7.3 gigabytes per second. On average, that can change. Hardware is changing every day. Then if you have an SSD, that's going to be 200 to 600 megabytes per second. If you're loading a model of 10 gigabytes, like you're waiting there and you're like, what is happening here? If you have an HDD, that's about 80 to 160 megabytes per second. So if you think about the stuff that goes into a server for these massive models that have 600 plus gigabytes in size, like just imagine how long it would take to load one of those models if you don't take your time to pick the best hardware for the requirements that you have. Okay, so the other stuff that happens is that the user comes in and it sends a response. Then the pre-filling happens. The pre-filling is when we start calculating what tokens do I need to pay attention to. So we start creating matrices and multiplying matrices. And then the KB cache gets created. The KB cache is going to also live in RAM. And then we're going to use a feed-forward network. So we're going to pass more matrix multiplications. We're going to pass it back here. And then we're going to go to the decoding stage. So what's happening here in this, when we start doing all those matrix multiplications? So we go from storage, we go to RAM, then we take a couple of the weights and then we put them, the ones that we need based on the calculations of attention and the KB cache, and then we put them into the L3 cache. Then it comes down, so usually what you have in modern chips is that you have the CPU chip and then you have the cores. So let's say you have 6 cores and then you have an L3 cache that is going to be shared between different devices. Then that goes down to the L2 cache. And then here we have the matrix multiplications. They're rather large because we can fit a little bit more in the L2 cache. Then we go to the L1. So we get smaller and smaller tiles until we get to the register and we get tiny, tiny tiles. I think it's 64 KB, a decent register size today. I think it is. I might be wrong. So then we send the results back and infrequently used values. Then we evict it. I think the correct word to use when you're sending stuff up the layers of cache is eviction. Then we send it back, then back the results, and then we decode the results. And then the tokens that we use when we train a model with a specific, in a specific way in which it could respond, then is by attending to specific tokens. Start of the prompt, end of the prompt is a special token. Start of the answer, end of the answer is another special token. And then there's another one called EOS, it's called end of sentence. So that's when it's saying, I am doing fine. And so that's kind of a representation of how to think about what is happening under the hood, why so many people decide to go with C++, because with Python, it's not as straightforward to access this level of hardware. Okay, so pixels or word tokens, it doesn't really matter. It's all matrix multiplication at the registers level. Here's another way of looking at it. This is another, I don't know why it's, I think it's the aspect ratio. So let me see if I can make it a little bit. Okay, there you go. Now you can see it. Fine. Okay, so we have the storage. We read the weights. They go into RAM. We load a portion of the weights into the L3 cache. We send them to the L2, or they are shared among a thread pool. The thread pool, the GenV is called generalized matrix multiplication. This is what is going to happen inside of the registers. So we do matrix vector multiplications. We accumulate the results, we store them, and we get the output vector back. We evict them back to the L1 cache, L2 cache, L3 cache, and so on. It doesn't seem like it, but it took me 3 weeks to be able to come up with that. Not knowing anything about hardware. I made that in February. So then when we get to the GPU level, we have something similar, but the GPU in this sense is much better than the CPU in terms of computational power, because you have a lot of workers, you can spread things like aggressively, you can do aggressively parallel computations, but then at the same time, the CPU is also very, very good at other stuff. So you have a similar setup where you have the whole system, you have the storage, you load the weight into the system RAM, and then they go into the GPU global memory or the VRAM. So you fetch data chunks, and then this goes into the GPU device, and then you have the GPU L2 cache, where you send it to the shared memory and load a chunk in the registers per thread. Then you have input activation, so remember that it's a blob of numbers, and we're taking what we need of that blob of numbers to be able to do these matrix multiplications. We get to the matrix operations in parallel in what is called the tensor cores. And then the registers and the shared memory, we store the partial results here. We evict them back into the shared memory, and then so on. But now, just imagine that there's just millions of different little workers here, and that is why you can do so much more, even with a tiny GPU than without any. Okay, but LLMs today can run on anything. So we're talking about from the perspective of a laptop, a computer, or even hardware that we will put that we will have on a server, that we will rent in a server. But and I started with the example from my personal computer. So what about where else can we put it? So we can also put them in the cloud, and that is usually where the biggest ones run. You need about 10 GPUs of the H100s today to run the latest DeepSeek R1 model. I believe it is. There's different companies do it in different ways and with different setups, but that amounts to about, I think it's about $50 per hour to rent all those GPUs, maybe a little bit more. So you calculate that times 100, times 24 in a day, times 7, times 52, and then that's a lot of money, especially if you don't have just one model hosted, but you need several. You need a cluster of GPUs to be able to run copies of those models. So it is expensive, and you can only imagine that by charging $20 to people, they're never going to reach a level where they can pay for the full cost of running a model. It is the moneymaker is when you use their APIs. And I think the person that came up with charging per token is a freaking genius. So because now there's no limit to what we can charge you. You consume this much, you pay this much. So every token that gets generated, they charge you, different companies charge you differently. You will see it as token inputs per million. So I think the latest model by Anthropic is input tokens. So things that you send into the model are going to be about per million tokens, $10, and then about $15 per output token, what the model gives back to you as a response. So now we're talking about in a day, you could easily get through 1 million. And if you run a company and you're using these LLMs, and now you $25. So you pay that monthly fee tens of thousands of times over if your company runs completely on these APIs. Raspberry Pis. So something that we are developing at Menlo is our Menlo Pi, and we are optimizing what we do with Cortex to be able to put models in our own Pis, because our own Pi is going to be inside a robot, and we want to provide the software and the hardware for robots. So the other one is, what did I write here? Personal laptop, yeah. And then the commonalities between all of these ones is that you need a motherboard, you need storage, you need communication, you need all the stuff that we talk about for a robot. The only thing that we're missing here is the sort of the body of the robot. So we're getting there in a non-linear way, but we're getting to the robot. So even on Edge, Arduinos, there are people running models in Arduinos. So this is the other big important piece about why C++ is that you need a Python runtime to be able to run Python inside a device. And that usually assumes that there is an operating system in it. But what about devices that don't have an operating system in it, and you have to package the model and everything else with the bootloader and put it into that little device? So that's another reason why we make that choice. And then, so how do we put models on edge devices? There's 3 frameworks right now to be able to do that. One is Executorch, which is a different variation of PyTorch, and it was created in 2023. It's C++, a lot of it, and then the percentage of Python is about 43.9. So it's very much the two. And then, I'm not going to read the fun fact. LiteRT used to be TensorFlow Lite. It was created in 2007, and it was TensorFlow Lite. I think because of the popularity of TensorFlow has gone down so much in the last few years. I think the rebranding was strategic. I think it is predominantly C++, yep. And then I think it has a tiny bit of Python, the LightRT. The other latest one is Transformers.js. This is very, very recently. It was created by a guy that was at university. I don't know the full story, but I think he was just on the side, just coding. And now he got hired by Hugging Face, and he is working full-time he's from South Africa. He's working full-time at Hugging Face, developing Transformers.js. And it allows you to have anyone here heard of web GPUs? Yes, it's a layer of abstraction across all of the GPUs that you might have in your machine. So it's actually quite nice. I think it leverages different APIs like Vulkan and a couple of others. So similar to OpenGL, WebGL, and so on, but kind of like the latest version, the bleeding edge, you can think of it. The percentage of C++ code is very minimal, but they do use ONNX, so they do have some C++ in it. And then Python, there's no Python, there's just TS. So recap, LLMs have massive requirements, but hardware is keeping up. Different devices are able to hold different LLMs in memory. Smaller models are getting more capable by the minute. I haven't even shown you this one, but I will in the next section. And then AI, to some degree, is lots of matrix multiplications, or matrices multiplication. And C++ let us handle the hardware and get fine control of it. So Cortex.cpp. So the tool that we have been developing at work. What is the current architecture? So the current architecture, we have different bits and pieces. We have a CLI and we have a server. We also have a data layer that is composed of files, database, logs, and models. And actually, to do it a bit of justice, here it is. So at my company, we have different teams. One of them is working on the desktop app that I mentioned. Me and a couple of others are working on Cortex, and then a couple of other people are working on the robotics, and another group is working on the Menlo Pi. So there's a lot of us, and then there's marketing as well. So go and check them out and check it out if you want to try it out. There's also different tools that we compete with, but this is fully open source. We're not planning on making any money for this. This is for us to be able to put models on devices, and especially devices that we are going to create. So, okay, so back here. So we have the CLI, and the CLI has a Docker style sort of developer experience. I'm going to walk you through a little bit more of that in a little bit when I give you some examples. We connect to the Hugging Face hub to be able to download models, but you can also point it towards your own model hub in the config file of each model. We also manage engines, and this is the biggest difference between us and another provider, for example, like Ollama and plain Llama CPP. We also have a server, and we have a server compatible with the OpenAI API, but we added our own flavor to it as well. So I'm going to walk you through what that means or what that looks like in a little bit. So this can be split too, I mentioned, in a server and a CLI and a config file where you can manipulate different things about the tool. So the way we handle dependencies is we use a VC package. Anyone here uses it? Okay, we have one person. We're trying to get rid of it. And I told someone here that works on it or that works with the team that develops VC package at Microsoft. And yeah, so the conversation ended there. So we're using CLI 11 for the CLI, and we use Drogon for the server. Okay, so the CLI. So Docker style functionality, easy to pull models, run OpenAI compatible server, switch. Okay, so Cortex-V. Check out the version that you have. Cortex-help. Very common stuff that you will find anywhere. When you get the models, you get to something that industry has started to adopt is to be able to call the model that you want and then the level of quantization that you're going to be using, if the model is going to be a quantized one. So we have adopted that as well. And then when you download a model, you also usually start the server. And you get three things with the model. You get the model gguf, the file with a blob of weights and a bit more information. And then you also get a model.yaml, something that dictates or allows you to tweak the configuration of that model, the context length, the temperature, which determines whether the model should be very creative with its answers or not creative at all and try to answer your question with the most probable word after each. So, so we download this. Those are the three things that we have, and then the metadata with how the server is going to use it. And then we have the model hub. We leverage the Hugging Face hub, but you can use any kind of hub that you want. And I'm going to show you where you can tweak that. So when we run the models, we can do Cortex run tiny llama, and then it's going to start up a chat in the CLI. And then it's going to say, so I was talking to Tiny Llama just before coming here, but he got a little bit crazy and seductive with me, and I didn't like it. I said, what's up? He said, what's up, Hans? And I'm like, whoa, what's going on? Stop it. And he said, your wishes are my command, literally. And I'm like, I cannot do it. So I went on to the next one. Engines list. We started supporting 4 different engines. Llama CPP being the default one, TensorRT LLM, which is a tool also with Python bindings, but mostly CUDA code and C++ code. So we allow you to bring it into Cortex and then run models on top of it, especially if you are planning on running things on NVIDIA GPUs. Then the third one is ONNX. And then the fourth one was bespoke Python code that you could bring into Cortex. And now we're redesigning what Cortex will look like. And I'm going to show you, bless you, I'm going to show you what that's going to look like in a second. So when you have the engine, you can install a new one. In the current version of Cortex, you can uninstall it. If it's TensorRT, ONNX, and so on, you can update them to the latest version if the library has changed. The trickiest thing with TensorRT LLM is that CUDA is very annoying with what version you have in your system. And if you don't have the one that it's expecting, then it's game over. Cortex engines use, if you are going to load one, because you're going to be using that one, engines load and unload. Okay, so the chat components, this is where we talk about the GGUF, which is the most important thing of how do we run these models locally. So the GGUF file is composed of a lot of stuff. You can find more information about this in Hugging Face docs, Hov GGUF. And what you have here is that you have some sort of like the 4 bytes for the magic number, GGUF. You have the version, currently number 3. You have 8 bytes for the tensor count. So how many tensors do you have in that file? Then you have 8 bytes for the metadata, the KV count, the number of metadata key value pairs. So the things that you have in the file, you can put a little bit more than what you have here for the GGUF file. And then you have the metadata with the metadata KV count, key value pairs, and so on. So here you have the general architecture. So the model could be Llama. Llama is a dense model. That means that it has a lot of layers and it uses them all when it needs to make a prediction back to you, when it needs to give you an answer. The other approach that it has become quite popular today is something called mixture of experts. Mixture of experts has different models, kind of like in the same file. And then you have sort of a orchestrator that sends the response to the most likely model to give you the best answer. So active parameters is going to be the ones that are loaded at any point in time in memory. And that's why it's not a dense model. You only have you have all of these experts, they might be in memory, but they're not being used at the same time. So you can be a little bit more strategic on how you manage your model. Okay, so you have the general name, the context length. These are 4,096 tokens. So that's going to be equivalent to, maybe a 30-page report or so. It's not a whole lot. The general file type, tokenizer that you're going to be using. This is extremely important. If you pick the wrong tokenizer, when you send a request to the model, what's going to come back out is gibberish. So it's going to be in bytes. And then you have the tensor info, the count values. So the dimensions, the type, the offset, and so on. And then you have the rest of the file is the actual values, the actual tensor. So it's a very clever thing. And this was created by one guy. It's my understanding of it. His name is, they call him Gigi. So that's what GGUF. Okay, so memory. Under the hood, if we use Llama CPP as the default engine, and under the hood, Llama CPP uses mmap, which is a low-level system called POSIX standard with Windows equivalent like map view of file, which is often used in high-performance C++ applications to handle files effectively. But what does that really mean? What that means is that when we have a traditional file read, we have the process space, and then we have the operating system kernel space. So we read in the data, and it goes into the storage. So we have the GGUF model file, we have the kernel page cache, and then we have the RAM buffer, the full copy of the whole thing. So everything goes through sequentially, and then with the typical application, you might have slower startup, higher initial RAM usage, and manual buffering. But what happens with the GGUF file is that now you have, using memory map, now you have the operating system and the kernel. So you have the storage here with the GGUF file, which might be quite large, and then you have directly the physical RAM. So what's going to happen is that this is going to be used in the virtual memory, and it's going to have a map to where the tensors are at. And when it needs them, it's kind of like it's fakely or vaguely in memory, but it isn't. So when it needs them, like it knows exactly where they are, and then it just brings them in. And then, so here you have the llama CPP process, and it has that. So the startup is incredibly fast because it's kind of like faking that it has it all in memory while it uses what it needs by pulling stuff from this virtual memory. So the way to think about it is that step 1 and step 2, the process calls mmap and telling the OS, I want to access this file as if it were in memory. So the OS sets up like pointers in the process virtual's memory address space to correspond to the file's location on disk, but actually doesn't load the data yet. This is why it is so fast and why so many companies are opting, if they are doing anything local with AI, they're opting to use llama CPP. Step 3 and 4, when the llama CPP process tries to access the part of the model, the weights, the blob of numbers, then for a specific layer via its virtual address, the CPU triggers a page fault because the data isn't actually in physical RAM yet. And then the step 5, 6, and 7, the kernel intercepts the page fault. It figures out which specific chunk, the page of the model file on disk corresponds to the requested virtual address. It then reads only that page from the disk into the physical RAM, which often used in the page cache, and then it updates its table, so the process virtual address now points to this physical RAM location. So the process execution continues seamlessly, and this is like the genius stuff about this. Like maybe we'll see something 10x better next year, but this right now is working really, really well for running AI models locally, and in particular, running AI models in small motherboards, small devices that we're going to put inside robots, what we call the brain. So when we talk about the model management, we can list the models that we have, and then we get the configuration file. This configuration file is going to live inside your home directory, and it's going to have information about the model. And so when was it created, the context length. Sometimes you can put something larger than this, but if the model doesn't support it, it doesn't matter, you're not doing anything wrong. It's just going to pick the max one that it has. Then there's going to be a lot of information here, but you can point to where you're going to find that model at if you put it into a different location, the max tokens, and so on. So this is the important thing that I mentioned earlier. When we do fine tuning of a model, we instead of giving the model the whole internet, the whole web, and say predict the next thing in this file, we now instruct it or train it so that it can give us useful answers back. And the way in which we do it is with special tokens, where we say, hey, this is your command. This is like your 10 commandments or whatever. And then in the next one, we're going to have, this is the prompt from the user. And then this is the response from the assistant. This is what you are going to, this is when you start talking, when you start predicting a response, an appropriate response to the prompt of the user. And then you're going to stop once you find this special token in the sequence. So that is, how to put it, this is critical for running anything locally, because every model requires a template, even like models from 2 years ago, even models from today. So then we assign each model to an engine, and then when you run it, Cortex is going to know what is using, what it needs to use behind the scenes to be able to run your model. Okay. So in the models perspective, we can manage them in a similar way to the engine: start, update, stop, import sources, and so on. So when we talk about the server, by default, your server will start at port 39 to A1. And if you navigate to it, you're going to see a nice documentation site powered by Scala. So I think that the reason I put that there is because I thought that the creator of this stuff was Australian, and I live in Sydney. So I was like, oh, yeah. Okay, so you start a server, then you're going to get this nice documentation. You can actually prompt Cortex from the documentation, which is really nice. So when you use the server, you can start the models with straightforward code request. You can talk to the model in a similar way in which we saw before. So we kind of like, this is kind of like the setup to be able to say, you are the user, this is the user sending you something. So the next thing that comes back is going to be a response from the assistant. So I said here, tell me a funny story about a C++ conference, bring robots into it. And he said, there was an annual C++ conference that took place annually in the middle of nowhere, far from any major cities or tech hubs. The conference featured a wide range of talks and panels on various topics related to C++, including programming languages, software development, design patterns, and more. One year, a robot was invited as a keynote speaker. The robot was an enormous mechanical behemoth that could move across the stage effortlessly as it took the center stage, the audience, blah, 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 blah. So it's actually quite funny. And the fact that this thing is tiny and it was able to come up with something coherent, I think is fantastic. And this is an old model that I used it because it's the simplest one to, or the easiest one to sort of like pull and then start using. Something to keep in mind, when you put stream true, you're going to get a JSON blob for every single token. So you're going to have to parse out the response of the assistant to be able to get something coherent inside an application. So something important to keep in mind. So the extras around OpenAI compatible API are hardware management, flexible backend, local on device. That's the stuff that we're doing. So what's the goal of Cortex? Why do we create this thing? Why do we have different engines? Why do we have different models? Why do we manage different, why do we manage the hardware of the host of the operating system? And that is because we want to be able to put AI models, especially smaller models that fit in something. It doesn't have to be a Menlo Pi because we don't even have a product in my company. We don't sell anything. But if we put a Menlo Pi or Raspberry, we're testing things with Raspberry Pi, Orange Pi, Banana Pi right now, and we put it inside a robot. Can we make it so that we can control the limbs with a token? So you can think about it in this way. If we have a token that says index finger or pinky and whatnot, and we say, you are going to have to make a movement, and the output that you have to give me back is a percentage for how much should you move this finger here, this finger here, this finger here. And this is something that we are doing already. So I'm going to show you a quick example here in just a second. So Cortex V2, the thing that we're doing now is going to have different backends for local models, similar ones that we're using. I don't like ONNX, but I put it here regardless. We're going to provide mobile and edge backends, like the one that I showed you earlier, Executorch, Llama CPP for executable files with something called Llama file, and then different container images if you want to go to a remote instance. Now, when you pull in a model locally, you will be able to benchmark the model and be able to say, actually, this is not the best one for my machine. Or can I optimize it even further? Can we push the model back into the hub? Can we install any new stuff that we might want to use alongside that model? Can we quantize it to a smaller version to be able to use it better inside a robot? Can we load something else? Can we add a different backend? Can we create evals? Can we build an image and then push it to the cloud? So that's sort of the V2 of it. So if we assume robots will have a motherboard, Wi-Fi access, run Linux, have a decent sized memory, then can we move faster with Python and C++? So we are also adopting in the next version. We're going to keep the core of it, C++, and then add nicer Python bindings so that we can move faster at the topper layer, and then also continue doing bespoke stuff at the lower level. So can we go from the developer to the robot to the cloud and enable different things? So, and now for the last bit, I wanted to show you what we have for, it was meant to be here. So the things that Cortex powers today, one of them is our sister product. It's called Jan. So if you want to run models on device right now, it is fully connected to the Hugging Face Hub, and you can run any model that you can imagine on Jan right now. We are about to launch at the end of May V2 of this. This is fully open source, free to use. Take it, sell it, do whatever. I actually think there's a couple of companies already selling a version of this. The next version of it has mobile support, and it comes out at the end of this month, end of May, mobile support. So you can have your models inside your laptop and then potentially connect to them via your phone if you're at home, if you're anywhere. So there's a lot of really cool use cases that we're testing, and this is all to be able to enable robots to run all these models with different use cases in the future. So there's Jan. Something else that we are doing. Where's my presentation? Something else that we are doing is that we have Ichigo. So Ichigo, and I swear to God, I thought I had these videos here. And so no, I'm not going to be able to get it. I can't remember where it's at. Okay, so there's a model that we call Ichigo, and it allows you to do text. So it allows you to talk in real time. So to the model that is loaded. So you have a transcriber in real time passing in the tokens of what you're saying to the model, and then passing tokens back to you. So we want to be able to talk to robots. So we're developing different modalities so that we can put them inside of Cortex. And then another one of the recent ones that we released was Alpha Space. So Alpha Maze is the first one. So I mentioned the stuff about the token. So if the tokens are the source of knowledge of a model, what can we do by building up different abstractions and teaching a model how to navigate mazes, or a robot how to navigate spaces inside a home, inside a warehouse, inside a factory, and so on. So we've been doing a lot of work around playing with different tokenizers and fine-tuning models to different devices, to different environments. And this is one of them, where we train a model to navigate mazes. And then it figures out how to go from one. Yeah, so we give it a starting point, and then we teach it in specific ways after giving it a prompt. Hey, you should be able to move from this place to this other place. Now, the tricky piece, if you have noticed, is that these are squares. So as of right now, this is kind of like, it's not super impossible because it's not an open-ended area like right here, for example, but that's the first step. Can we represent something as squares and then see where we can go next and see if we can grab that momentum, literally. So this is another one that we have. This is all open source. All these models can be downloaded. And what we have here is a simulated environment where we created, we have a robot arm, and then with different tokens, we train a model to provide back action tokens, where we teach the model, we say, hey, this is something that you need to move on the table, and then you should put it on top of the other stuff. Imagine it being plates, it being a meal, and so on. So we had a lot of fun with this. This is also everything that I'm showing you is the open source stuff that we're doing right now. So it did it successfully, and this is all with a tiny 1B model that can run on your phone even. So imagine being able to control a mechanical arm at home, starting the meal from your phone. So that's kind of some of the places that we're going. And I have about one more slide or two more slides left. Let me see. Okay, so the last one that we did was about 3 weeks ago, and it's called, about a week ago, and it's called ReZero. And it restarts from zero when you give it a search query, and it has access to the internet. So this is a really cool model because it allows you to take advantage of the internet. And if you give it a query, what are the best-selling books of blah, 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 it's going to go off to the internet and try to find an answer. And it won't stop until it finds the answer. Like, it literally sometimes will go into this massive loop because it is a tiny model, but it will not stop. So Menlo Research, who are they? What do they do? Links to it, and then he found it. So it's going to continue. So when we give an instruction to a model, make this meal, a robot, make this meal for us by the time we get home or whatnot, and it cannot find the recipe, should it give up and then just not make anything? Or should it make something else? I don't know. But we're playing with these use cases because we think we have to sort of get creative if we want to build software and hardware that somebody can just buy anywhere and then or get and access and put it inside a robot and control it for themselves. And then, so the trade-offs of all of this, of moving into Python now, Python is slower than C++, and that's not and that's why not just Menlo, but many robotics companies use both, because allows you to go faster at the same time. So I think I meant to put something else here, but there's a lot of moving parts to a robot, and by targeting the board plus the software, we're looking to capitalize on at least two of the verticals. You might see the chassis as well. We have a bunch of chassis of different robots that we have purchased that we're testing these models on. And it's been pretty cool. The rapidly changing landscape equals we welcome the change, at least for us. So the research, we're hoping for better models. So this is the one that I was going to show you. This just came out yesterday. So DeepSeek V3 and GPT-4o, some of the best models out there. And then Qwen 4b is almost at par with GPT-4o. And these are different benchmarks, so take it with a grain of salt. 73.8, 11.1, 66, 65.6, 7.6. So it is mind-blowing that this fits on any laptop today, on any computer. And it is a tiny, tiny model. So this came out yesterday. This is not even their biggest one, and it's just absolutely crushing it in all benchmarks. So I think a year from now, we're going to see even better models than what you see now. And this is just the beginning. So better hardware as well, we're hoping. So the Columbia engineering team collaborated with a couple of researchers, and they have developed a 3D integrated photonic electronic chip that boasts a high density of 80 photonic transmitters and receives within a compact chip footprint. So what the thing, I didn't understand anything about that, by the way. The thing that blew my mind was that this platform delivers a high bandwidth of 800 gigabytes per second with exceptional energy efficiency. So I don't know when they're going to release this. I saw a couple of demos of their hardware, and that stuff is incredible. So just imagine what's going to happen a year from now. So this is you can find their research and their board, the details of the board. So this just came out last month on the Columbia Engineering website. We're hoping for better robots. I thought I had a robot here to show. Better software as well. Where's my software? Okay, so what's next? So revised version of Cortex, at least for us, the Menlo Pi, more experiments with tokenization, simulation, and then build. So thank you very much. That was my talk. And I realized that I didn't even stop and say like, hey, does anybody have any questions? Because I think I had over 150 slides, but anybody has any questions? Any thoughts, any comments?
Oh, well, I noticed that you talked a bit about wanting to use a single board computer to run AI on robotics. You mentioned specifically different Pis. I was curious why you didn't mention like the NVIDIA Jetson series at all, which is specifically designed for AI.
So I think the reason for that one was that, let me say two things. One is we are partners with NVIDIA, and we have a very close relationship with them. I think we started focusing more on boards without a GPU in it. Like, can we maximize the performance of these models in the thing that we're most likely to see out there? So we're not going to see a lot of robots out there or a lot of computers with an NVIDIA GPU by default. We're going to see a lot with CPU only. So that's why we were targeting first, like, can we get the lowest performance ones to run these things and then go to the better ones? Because we can assume a lot of stuff from the better ones, but not a whole lot from the small ones.
I see.
Good question. Anything else? Well, thank you for spending an hour and a half with me, everyone. I hope you found it useful, fun.
Definitely.
Nice. Thank you very much. All right.